Today I will be reviewing the topic of chemical equilibriums and going into further detail of how the equilibrium constant stays constant throughout an equilibrium reaction. You are most likely familiar with the term equilibrium, the conditions existing when the forward and reverse reaction of a chemical reaction proceed at equal rates. In some cases, the reaction has enough kinetic energy to overcome the activation energy of the reaction and flows in either the forward or reverse reaction. At any time in a reaction, the reaction quotient is used to describe the nature of the reaction mixture. At equilibrium, we can show a similar expression of the equilibrium constant K in terms of molar concentrations of the starting material and products. So in this presentation, we will be looking at the concentration of reactants and products when the state of equilibrium is reached. As you will soon learn, these values of concentration will not remain constant throughout the reaction. However, the equilibrium constant will remain the same. So as a reminder, the equilibrium constant expresses the relationship between the products and the reactants of a reaction at equilibrium. In order to express this value numerically, one must take the concentration of each of the products, and then you will multiply them by each other, and you raise the concentrations to the mole ratio or coefficient. Then you divide this by the concentration of each reactant, multiplied by each other, raised to the power of the mole ratios or coefficients. So you may be wondering, what does the equilibrium constant mean? And the equilibrium constant can tell us a lot about certain reactions. When the equilibrium constant is less than 1, this means that there is a higher concentration of reactants than products and favors the production of reactants. Hence, in this case, move to the left. When the equilibrium constant is greater than 1, this would imply that there is a higher concentration of products than reactants and favors the production of products. Hence, in this case, move to the right. Lastly, if the equilibrium constant is 1, the numerator and denominator are at equal concentrations, and the forward and reverse are equally favorable. One important property of the equilibrium constant is that despite the varying amounts of starting material of a reaction, the equilibrium constant will remain the same. This property can be easily remembered, hence the word constant in equilibrium constant. That is to say, at a given temperature, the ratio of the rate constants for the forward and reverse reaction are the same. Now we can also compare the equilibrium constant to the reaction quotient to predict the direction of the reaction. When the equilibrium constant is greater than the reaction quotient, the reaction will move to the right. When the equilibrium constant and the reaction quotient are equal, this means that the reaction has reached equilibrium. When the equilibrium constant is less than the reaction quotient, the reaction moves to the left. Now, I don't know about you guys, but this image above really helps me visualize how you can interpret the equilibrium constant in relation to the reaction quotient. As we talked about the importance of the amount of reactants, we can take it back to an explanation of the incompletion and reversibility of chemical equilibrium reactions, which was discovered by the French chemist C.L. Berthollet. So Berthollet's ideas were developed after Bergman, who was another chemist, stated that reactions always come to completion and that they take place only in one direction. Now, if you know anything about equilibriums, we know that this is not true. So Berthollet's ideas came to be on a trip. He accompanied Napoleon's expedition to Egypt, and he was intrigued by the natron lakes that lie in a large depression west of Cairo, observing the continuous formation of sodium carbonate deposits on the edge of these sodium lakes. This reaction occurred between salt and limestone, which is sodium chloride and calcium carbonate, to produce soda, which is sodium carbonate, as well as another product of calcium carbonate. And we can see this expression just below the image. And so basically what was surprising is that this happened to be the reverse reaction of the one that the chemist knew. Berthelot tried to explain this unexpected reaction, taking into account the great quantities of the two reactants present and the continuous removal of the products. In point of the fact, the sodium carbonate formed a crust around the edge of the lake, and the deliquescent calcium chloride seeped away into the ground. Berthelot brought attention to the mass playing a role in affecting the results of reaction, and that is to say, the mass of the reactants could reverse the reaction predicted by the scale of relative affinities. In addition, a relatively large quantity of substance with weaker affinity may exert a force that can surpass the force of the substance with greater affinity. He also brought attention to the fact that any displacement reaction was never completed and that there was an equilibrium state between opposite affinity forces. These forces depended on the difference in their relative affinities and the quantitative proportion. And the direction in which a reaction takes place was determined by the quantitative proportion of the chemicals involved in the reaction. We can think about the quantitative proportions of the reaction in the following example. So if this discovery was a little difficult for you to visualize, we can illustrate this in the following example. So we're going to use a different equation. In this case, we're going to look at the equilibrium of dinitrogen tetroxide and nitrogen dioxide. We can manipulate the following reaction to start with different initial amounts of concentrations and see how, based on this theory, the equilibrium constant will remain the same. The equilibrium constant of the dinitrogen tetroxide and nitrogen dioxide reaction at 298.15 kelvins is theoretically 6.53 plus or minus 0.03 times 10 to the negative 3. In the following chart, there are varying initial concentrations of dinitrogen tetroxide and nitrogen dioxide, which will lead to different concentrations at equilibrium. Despite these different values, the equilibrium constant remains approximately 6.53 times 10 to the negative 3. I will demonstrate how the concentration at equilibrium will be obtained using the initial concentrations in experiment 1 and 5. To begin the first experiment, we will begin with 0.05 molar of dinitrogen tetroxide and 0 moles of nitrogen dioxide. If we calculate Q in this scenario, we see that it equals 0, which is less than the equilibrium constant. So therefore, we can conclude that the reaction proceeds to the right to produce more products. As you should be familiar from Module 8, we can express this reaction in an ice table as the following. So we can put in place our known values of initial concentration, and since we know the reaction proceeds in the forward direction, we will be losing some of the reactants to form more products. So we can put a negative X for dinitrogen tetroxide and a positive 2X for nitrogen dioxide. Now in the last row of the ice table, which is the equilibrium, we can add the initial concentration with our change as the following. Now we can set up our equilibrium constant expression as the following. So the concentration of nitrogen dioxide to the power of 2, because there are 2 moles present in the reaction, over the concentration of dinitrogen tetroxide. Then we can expand the expression until we have a quadratic equation in order to plug into the quadratic formula. Now, after putting that through the quadratic formula, we are left with 2 values of x. And so we have to see which one makes the most sense. Obviously, negative 0.009896 can be excluded because it was result in nitrogen dioxide being a negative concentration, and that just doesn't make sense. And then we can assume 0.00826 is our x value. Then to finish up the problem and write the concentration of dinitrogen tetroxide and nitrogen dioxide by subbing our values of X into each expression. So for dinitrogen tetroxide, we take 0.05 and we subtract 8.26 times 10 to the negative 3 to get a concentration of 0.04174. And then for nitrogen dioxide, we just have to multiply the X value by 2 because there are 2 moles of nitrogen dioxide. And then we will end up with a concentration of 0.01652. If we reference the chart again, we have obtained the same concentrations at equilibrium. And we can also check that we obtained the correct value by subbing the concentrations at equilibrium and solve for the equilibrium constant. So I will go through experiment 5 a little more quickly since you probably have a strong understanding of this by now. So first we will compare Q and K values to see which way the reaction proceeds. And since 0.225 is greater than 6.54 times 10 to the negative 3, we can say the reaction favors the reverse reaction and proceeds to the left. We can express this in the ice table as the following. And then solving for a quadratic equation, we can put this into the quadratic formula, and we will obtain X values of 0.0482 and 0.0283. And if we try both X values, 0.0482 makes the concentration of nitrogen dioxide negative, therefore the correct value is 0.0283. And finally, we obtain the concentration at equilibrium of dinitrogen tetroxide of 0.0530 and nitrogen dioxide of 0.0183. Unfortunately, we do not have enough time to show you how all of these values were obtained, but hopefully this table will help you understand that the initial concentration of a certain reaction will not affect the equilibrium constant, and that the equilibrium constant of a reaction is a set, never-changing value in a certain temperature. Thank you.